In this experiment, we'll be using a Geiger-Müller tube to measure beta and gamma radiation.
The tube has got a protective cover on the front, which if I carefully remove, you can see a very thin window which allows the radiation to pass in. This one here has had the end of the tube removed, revealing a central wire which is positively charged and a cylinder which is the negative connection. Every time the radiation comes in, it'll trigger an event which can then be counted by a machine.
Schools may have different types of meters, but essentially they all provide the same function: to provide the voltage to the Geiger-Müller tube and count the events.
Whenever you're setting up a radioactive source, you always make sure it isn't pointing at people. And a good setup is to use a retort stand with the radioactive source pointing downwards all the time and the Geiger-Müller tube at the bottom. Whenever you're using a Geiger-Müller tube, particularly if you're holding it in a clamp, it's very important to make sure you don't squeeze it too hard, because that too could damage the window.
For this experiment, use a pure beta source such as strontium-90.
I can get an audible representation of how much radiation I'm measuring. The first thing to do is to show that, unlike the alpha particles which are stopped by paper, the beta particles aren't. So putting a piece of paper in makes no difference at all. However, if I bring a piece of aluminium in, we can hear that the beta particles are completely stopped, because the range of beta particles is a few millimetres of aluminium.
What happens to the beta radiation?
As the beta particle enters the aluminium, it'll slow down, losing energy. In the end, it's likely to become part of the sea of electrons. The other thing we can demonstrate is the range of the beta particles in air, and if I move the source away from the detector, you'll hear that the count rate decreases. And notice that the range in air is significantly larger than the alpha particles, which was 2 or 3 centimetres. We're at tens of centimetres and still getting a reading on the counter. This time I'm going to use cobalt-60 as my gamma source. So I'm going to mount the gamma source above the Geiger-Müller tube.
That's quite a lot lower count rate.
There's two answers to that. The first is that the Geiger-Müller tube is not as good at detecting gamma rays. And secondly, the number of gamma rays produced by this source is quite low. If I put the aluminium in the way, the aluminium is not absorbing many of the gamma rays as they pass through. However, if I introduce some lead, it's only with a couple of centimetres of lead in the way that the count rate is significantly reduced, because gamma rays can pass through lead, but several centimetres starts to significantly reduce the number getting through.
Reduced but not stopped.
Yeah, to completely stop the count rate, we have to have several tens of centimetres of lead.
Why is it that lead stops it as opposed to another metal like aluminium?
OK, the aluminium itself is quite a light metal. Its density isn't very high, as opposed to lead, which is very dense, which will absorb the gamma rays as they pass through.
Handling the absorbers with the bare hands is quite safe. The problem arises if you're tempted to put the absorber close to the source with your fingers. So we always recommend that an absorber should be handled with forceps if you've got a radioactive source nearby.
What you see here are the 3 types of radiation streaming towards you. On the right-hand side here are the gamma photons. In the middle is the helium nucleus, the alpha particle, 2 protons, 2 neutrons. And on the left-hand side is the beta particle, the very fast electron. You'll notice that the gamma rays and the beta particles are almost travelling at the same speed. That's because the beta particle is travelling at a speed quite close to the speed of light. If I bring a piece of paper in, what you'll notice is the alpha particles are now unable to penetrate through. The gamma rays and the beta particles, though, can still get through. If I bring a piece of aluminium in, that's enough to absorb the beta particles, and they are no longer getting through, and there's no significant reduction in the number of gamma rays. If I bring in a large piece of lead, that is enough to absorb a significant number of the gamma rays, and the count rate drops right down.
Using the absorption demonstrations is a really useful way to check students' understanding of the penetrating properties of radiation.
The other thing that we can start to try and show with this setup is how the range of the gamma rays in air is linked to the inverse square law. So hopefully if I double the distance they are away, the count rate will go down by a factor of 4. So at the moment my source is roughly 4 centimetres away, and if I double that to 8 centimetres, the source will now be counting at about a quarter the count rate.